This video is going to go over an example of Newton's law of heating and cooling. It's very similar to exponential growth and decay, where you have something hotter than an ambient temperature, so it needs to cool down to that temperature, or you have something colder than an ambient temperature, so it will warm up to it. So for example, let's say we make a cup of coffee and it's 150 degrees Fahrenheit, and then we just let it sit at the room temperature of 70 degrees. We know the change in temperature of the coffee with respect to time is proportional to the difference between the current temperature and the temperature of the room. So Newton actually came up with this theory, which is amazing, and it works out, and it's true. So what does that mean? So the rate of change of the temperature of the coffee with respect to time, so that's our differential, is proportional to, so that's our K, but then it's the current temperature and then the temperature of the room that it's proportional to. So if I know the initial temperature is 150, and then let's say after 5 minutes it's still 125 degrees Fahrenheit, then a possible solution curve, if I were to look at this, would go like this. Now notice it kind of levels off here, and where it levels off looks like it's about 70 degrees, right? Like that makes sense. That's our ambient temperature, because that's the temperature of the room, okay? This should be ENT. So known parent functions here, this is going to be an exponential decay with a horizontal asymptote at 70. Let's use separation of variables to find this equation for t. So I have the change in temperature over time is proportional to the current temperature and its difference to the ambient temperature. I'm going to keep t minus 70 together and move it over. And then I'm going to go ahead and integrate both sides. When I do that, I get the natural log of the absolute value of t minus 70 here, and I get kt plus c. I have an initial temperature that is higher than the temperature here, so I don't need to worry about the absolute value bars in this scenario. And so if I take e to both sides, I end up getting t minus 70 is equal to, we do that nice CE to the KT trick here, which means temperature must be equal to some exponential function moved up 70. That makes sense. That's the graph that we just did, right? Right here. Okay, let's use our initial conditions to solve this. So I know that at t equals 0, my temperature was 150. And at time equals 5, the temperature was 125. So let's plug in here. Now be careful on some of the ones we did in the video before this. Your initial was your C, correct? But now we've moved this up. So now I'm going to plug in 150 equals CE to the 0 plus 70. When I subtract 70 over, I get that C is actually 80. All right, let's go ahead and plug in now over here. I know that 125 equals 80 e to the 5k plus 70. I'm going to subtract 70. So I would get what, 55 equals 80 e to the 5k. I'm going to divide 80 on both sides. I'm going to take the natural log of that to get rid of the e and then divide by 5. So k is equal to 1/5 natural log of 55 over 80. Plug that into my calculator. Now it's going to be negative because 55 over 80 is a number smaller than 1. I'm taking the natural log of that, and I end up getting that k is equal to negative 0.075 when I round. Okay, so my overall equation is going to be that T is equal to 80 e to the negative 0.075 T plus 70. And that's the temperature of the coffee at any time. Let's look at how we might want to solve this using an integrating factor. In order to do that, I would have to distribute my K. I could then subtract KT over here. I could then use mu to be e to the negative integral of negative k dt. Now, when I go to integrate that right-hand side, I kind of didn't give myself enough space here, and if you're taking notes in our notes packet, just take the notes that you need to. But essentially, I'm going to be ending up taking the derivative with respect to time of this product, and then I need to multiply it over here, which means I would have to do an integration by parts on this one. I don't know. I don't think I want to do that. Okay, I really don't think I want to do that. So in this case, I would use separation of variables. Okay, it is you're able to do it as a linear first order, but I just don't think that that's a nice way to do it. All right, let's look at the other way. Okay, so let's say we have an ice cube and it's set out in this room and left to just melt into a puddle. How does the solution change? So let's look at what happens when that's the case up here. Okay, so now I'm down here at like negative 32, right, at freezing, and then it's going to end up warming up to that 70 degrees. Well, in that case, I'm still going to have this as my solution curve, but you'll see I need to end up taking that e to the negative kt piece, right, that creates this, and then I need to flip it this way. Think about back in algebra how we flipped something from here down here. You made the front negative. So let's solve this and let's just see. So I know that that's still my solution curve. Okay, that doesn't change. What changes is where my initial condition is. Right? So now in this case, when I plug in 32 at 0, and I subtract 32 over, I get a different C. And that makes sense, right? If I have something, oh, sorry, that's negative 38. Oh my goodness. 32 minus 70 is negative 38. There we go. So if I have something that is below the ambient temperature, then it needs to grow, right, to the ambient temperature. Well, I still have a negative decay function, like that's still, this is still that like overall function, but I need it now to flip down. Well, I do that by making the constant in front of your parent function negative, right? So I know that T is equal to negative 38 e to the kt plus 70. Now, the k in this is going to be different because, and I don't have a second one in order to find it, so this is as good as I can get on this one. I more wanted to show you how the c is going to be negative and what it means. It's not going to be the same k because our initial temperature to 70 is smaller, and so that growth rate is going to be a different rate, or that decay rate, however you want to think about it. That constant proportionality is going to be a different one than when you start further away, because remember it's proportional to the temperature and the difference between the temperature and the ambient temperature. So if you start closer, then that K is going to be different than if you start further away. Okay, so that is how we do Newton's law of cooling. You do end up having two constants here. You have the C and you have your K. It's nice when you have an initial condition because then you can find C really easy, but just like before with growth and decay models, you would need a second number in order to find K for each and every situation.